Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we will discuss about 2π plus 2π cycloaddition reactions. As an usual practice, before starting today's class, we will quickly recollect what we have discussed in the previous class. So we started with understanding the cycloaddition reactions. So what are cycloaddition reactions? The addition of two unsaturated individuals resulting in the formation of a cyclic adduct is called as cycloaddition reaction. So the conversion of or the addition of two unsaturated systems leading to the cyclic adduct molecule is called as cycloaddition reactions. The reverse of this reaction is called as retrocycloaddition reactions, right. So cycloaddition reactions are governed by Woodward-Hoffmann rules. So how do we arrive at the Woodward-Hoffmann rules? So we have already seen the three theories which conclude the Woodward-Hoffmann rules for all the unsaturated systems in the cycloaddition reactions, right. Cycloaddition reactions happens with the unsaturated systems. Any unsaturated system, because of the presence of sp2 hybridized carbon atoms, will show you two phases. One is the above phase and the other is the below phase. If any unsaturated system is extending the orbitals from the same phase to form a sigma bond, then it is called as it is treated as a suprafacial partner. If an unsaturated system is extending its orbitals from the opposite phases or the different phases, then we call it as an anterofacial partner. So suprafacial partner will always retain the stereochemistry, whereas the anterofacial partner will not retain the stereochemistry. It will show the change in the stereochemistry, right. So after discussing the frontier molecular orbital approach, so the Woodward-Hoffmann rules are like this. So for a 2π plus 2π system, so the cycloaddition reactions, as we have discussed, if the unsaturated system is using both the lobes from the same phase, so it is a suprafacial partner. So if an unsaturated system is using different phases, so then it is an anterofacial partner, right. So 2π supra, how the cycloaddition reactions are shown, described, means on the arrow mark you have to mention the number of pi electrons involved plus the number of pi electrons involved in the second partner, and at the same time you also need to mention whether the first partner is a supra partner or an antero partner, and also the second partner, if it is acting as an supra partner or an antero partner, should also be mentioned on the reaction head, right. So 2π supra plus 2π supra mode of cycloaddition reactions are photochemically allowed. So these are photochemically allowed. Whereas 2π supra plus 2π antero mode of cycloaddition reactions are thermally allowed. So in brief, what you can see is 2π supra plus 2π supra or 2π antero plus 2π antero mode of cycloaddition reactions are photochemically allowed. 2π supra plus 2π antero or 2π antero plus 2π supra mode of cycloaddition reactions are thermally allowed as per the Woodward-Hoffmann rules. So as long as the two adding partners, combining partners in the cycloaddition reaction does not have any substituents at the termini, you need not to worry about the stereochemistry. So when there are substituents at the terminal carbon atoms of the individual partners, then the stereochemistry matters. So the suprafacial partner will retain the stereochemistry and the anterofacial partner is the one which is changing the stereochemistry. So for example, if we start with cis butene to butene. So, now the first one is a 2π partner and the second one is a 2π partner, right. Under photochemical conditions, so which mode is allowed? So, 2π supra, the first partner should be supra partner and the second partner should also be the supra partner. So, 2π supra plus 2π supra is allowed photochemically, and now we are checking the example of 2-butene. So, this 2-butene will give you two different products. So, this plus this. So, in the first partner, if you see, this is a cis molecule and this is also cis, right. So, the stereochemistry as it is supra individual is retained here. So, this is still cis. So, here also as it is a supra partner, so stereochemistry is retained. So, in this case as well, the supra as it is a supra partner, stereochemistry is cis retained and here also it is retained. So, what if you use the trans 2-butene? CH3 and CH3. So, this again under photochemical conditions is a 2π supra plus 2π supra cycloaddition reaction. So, you will be seeing this, where the stereochemistry is retained because this is a supra partner, and here also the stereochemistry is retained because it is a supra partner. In addition to this, you will also get this. So, this again is retaining the stereochemistry as well as this. So, these are the different types of stereoisomers you will be getting with the cycloaddition of cis 2-butene and trans 2-butene. What if I mix one cis 2-butene with another trans 2-butene molecule? So, if I try to add these two molecules under photochemical conditions, where the first partner is supra and second partner is also supra. So, you will be getting different types of products. So, that is because of the addition of the cis 2-butene, you will be getting these products. And so, because of trans 2-butene, as seen in the previous case, you will be getting these products. Along with these two set of products, you will also be seeing this one. Plus so, on adding one cis 2-butene and the trans 2-butene, in 2π supra plus 2π supra mode of cycloaddition reaction under photochemical conditions, you are able to see this many number of isomers as the products. So, similar is the case when you try to add stilbene molecules. Yeah. So, trans stilbene on cycloaddition under photochemical condition in 2π supra plus 2π supra mode, you will be able to see two products pH plus H and pH in 4:1 ratio, and this happens in benzene at 27% of the reaction, right. So, this is how it happens, and if trans stilbene, if you add it with so 2,3-dimethyl butene, 2-butene, you get this product, right. So, this gives us some information saying that all these 2π plus 2π cycloaddition reactions under photochemical conditions are supra plus supra mode of cycloadditions, right. So, what if we need to investigate the 2π supra plus 2π antara mode of cycloaddition reactions which are thermally allowed, right. So, generally 2π supra plus 2π antara mode of cycloaddition reactions which are thermally allowed are rare to be seen. So, they are not that frequent because one partner is a suprafacial partner, the other partner is an anterofacial partner. That means the anterofacial partner has to change its stereochemistry. How it is going to happen? Means the anterofacial partner, he should be perpendicular to the plane of the suprafacial partner. So, that mode of interaction where one partner is suprafacial and the other partner is anterofacial in 2π supra plus 2π antara mode of cycloaddition reactions. So, they have to approach each other in a perpendicular manner, and this happens only when there is no stereo congestion. So, and such kind of cycloaddition reactions, 2π supra plus 2π antara thermally allowed cycloaddition reactions are seen in the case of ketenes, cumulines and isocyanates with the olefin molecules, right. So, alkenes add up with ketenes or cumulines or isocyanates. So, what is the common thing in these molecules? Means there is at least one sp hybridized carbon atom in these molecules which decreases the stereochemical congestion, right, as a result of which it easily participates in the cycloaddition reaction which is 2π supra plus 2π antara mode of cycloaddition reaction, and it is thermally allowed, right. So, in this case the alkene acts as the suprafacial partner and the ketene acts as the anterofacial partner, right. So, how we will see these molecular models. So, this is a ketene molecule. So, if you see it carefully, this is the sp2 hybridized carbon atom and this is again sp2 hybridized carbon atom. So, connected to the oxygen. So, a double bond is there between this carbon atom and this carbon atom, and at the same time one more double bond is there with this carbon atom and this oxygen. So, this is the carbonyl carbon atom which is less sterically crowded, right. So, and the LUMO is located on this carbonyl carbon atom. So, this low lying LUMO molecular orbital, the LUMO molecular orbital on this carbonyl carbon atom is low lying. This one is there. So, now this interacts with an olefin alkene molecule. So, this is an alkene molecule. How the approach will be? Means if this is the ketene molecule, the bond formation, the cycloaddition takes place between these two carbon atoms and the alkene carbon atoms. So, this should be perpendicular to each other. This should be perpendicular to each other. So, if this is the ketene molecule and if you see the red color one or the orange color one is the bulky group, So, how it happens? The alkene or the ketene will approach each other such that the less sterically hindered carbon atom of the ketene, that is the carbonyl carbon atom, will be close to the more hindered carbon atom of the olefin alkene. So, the more hindered carbon atom of the alkene is the first carbon atom, which is having a bulky group, so shown by orange color. So, it will approach such that the more hindered carbon atom of the alkene is close to the less hindered carbon atom of the ketene, right. So, this perpendicular approach or orthogonal to each other approach will only facilitate the 2π supra plus 2π antara mode of cycloaddition reactions thermally, 2π plus 2π reactions thermally, right. So, this is the best example. So, first we will see how we are able to produce the ketene molecules. Ketenes can be synthesized in different methods. So, the easiest ones are treating the acid halide which is having at least one alpha hydrogen with a base like triethyl amine. So, this triethyl amine is a base. What it will do? It will abstract the proton and results in the formation of a ketene molecule C H R. So, this is a ketene. What if I do not have this acid halide, but I have an ester? So, again if the ester is having at least one alpha hydrogen and treating it with a base like lithium diethylamine or lithium dialkylamine, the same is the resultant. So, you will get a ketene here, right. So, if you have an acid halide with one more halogen on the alpha carbon atom and treating it with zinc metal, so you will be able to see the ketene plus zinc chloride will be formed. And again in the preparation of ketene molecules, you can make use of the pericyclic reactions. The electrocyclic ring opening of cyclobutene, so with appropriate structure like this, can also give us the ketene molecule. So, you will get ketene like this. So, an electrocyclic ring opening of this molecule, so you will get a ketene this way. So, that is how you are again using pericyclic reactions in the production of the ketene also. So, which will be further used in the cycloaddition reactions, 2π plus 2π cycloaddition reactions. So, as discussed in the cyclic transition state, so the largest group of the group attached to the carbon atom of the olefin will be close to the carbonyl carbon atom of the ketene. So, if this is the ketene having the largest group and the smaller group here. So, the olefin will orient itself such that the largest group will be close to the less hindered carbon atom of the ketene, that is the carbonyl carbon atom. Later, what happens? C double bond O. So, it will connect with this carbon atom this way. So, it results in the formation of a cyclic adduct molecule like this, right. So, when you see this here, the olefin is the suprafacial partner, and if you are considering the reaction between cis 2-butene and the ketene, let us see how the approach will be. So, this is cis 2-butene and this is a ketene, right. So, generally cycloaddition should take place here, resulting in the formation of a cyclic molecule. But how it will happen means, this is the olefin where the orbital is shown in the plane of the molecule. So, the ketene will arrange such that C double bond O, C, R group and hydrogen. It is perpendicular to the plane of the olefin, which is suprafacial. So, this olefin is supra partner, whereas the ketene is antara partner. Right. So, now as this is an antara partner, so lobes from the opposite faces should be used for the bond. So, this lobe is in this face, which is useful for bonding, and this lobe is in the other face, which is again used for the bonding. So, in the cyclic transition state, so this is the cyclic transition state. As we have mentioned earlier, the sterically less crowded carbon atom, that is the carbonyl carbon atom of the ketene, will be close towards the sterically more crowded carbon atom of the olefin. So, that is the case here. If you see here, this is the sterically crowded carbon atom of the ketene and it is close to the less sterically crowded side of the olefin carbon atom, right. So, this is what is formed in this next step. So, which is nothing but the cyclobutene adduct CH3. They are cis because the olefin has participated as the suprafacial partner, and R, this is H, and this is the thing. So, this is the cyclic adduct formed after the cycloaddition reaction of a ketene molecule with the olefin. The olefin is cis 2-butene. As this is suprafacial partner, it has retained its stereochemistry there. So, we will see one more similar type of example where the olefin OCH3 is adding with a ketene. So, as described previously, this is OCH3 and this is pH, right. So, interaction will be formed between these two lobes and these two lobes. So, you will be getting the product this way, right. So, which can be seen with the help of these molecular models. So, let us assume that this is an olefin molecule, right. So, this is a suprafacial partner and it contributes the homomolecular orbital. So, this homomolecular orbital is there. So, for an olefin under the ground state, because this is thermally controlled reactions. So, ground state you have to select the homomolecular orbital. So, psi 1 is the homomolecular orbital. So, the lobes are same on the same face, right. So, upper face is having the positive lobes and lower face is having the negative lobes. Okay. So, the olefin has to be taken this way. So, this is in this way. So, the two positive lobes are pointed towards you and the two negative lobes are pointed towards me, and this is the ketene molecule. If you can see, this is the ketene molecule and LUMO should be selected in the ketene molecules, right. So, LUMO should be selected from the ketene molecule. So, how the interaction will happen between this olefin and the ketene means they are perpendicular to each other. They are perpendicular to each other. This is an anterofacial partner and this is a suprafacial partner. So, as this is a suprafacial partner, it utilizes both the lobes in the same side, and this is an anterofacial partner. So, therefore, it utilizes the lobes on the opposite sides, right. So, how it will happen? You see. So, this approaches in a perpendicular manner and now the interaction is like this. So, the ketene carbon atom, yeah. So, these two lobes, positive lobes are interacting with each other to form a sigma bond, and at the same time these two positive lobes will be interacting with each other to form a sigma bond. So, the olefin is a suprafacial partner and the ketene is an anterofacial partner, right. So, hope you understood the stereochemistry, how the 2π supra, 2π antera mode of cycloaddition reactions are happening in the thermal conditions. So, in the next class, so we will consider the examples of so many cycloaddition reactions involving the ketenes, both intramolecular cycloadditions involving the ketenes and also the intermolecular cycloaddition reactions involving the ketenes, and some other examples of 2π plus 2π cycloaddition reactions. So, now we will discuss some more examples related to the 2π plus 2π cycloaddition reactions, in which some of them are thermally allowed reactions, that is 2π supra plus 2π antera cycloaddition reactions as discussed in the previous class. So, it is peculiar reaction happening under thermal conditions in special cases with ketenes, cumulines or isocyanates, and some of them are general 2π plus 2π cycloaddition reactions which are photochemically allowed, that is they are 2π supra plus 2π supra cycloaddition reactions. So, let us start with thermally allowed 2π plus 2π cycloaddition reactions. So, as discussed many times, so thermal 2π plus 2π cycloaddition reactions are allowed only if the first partner, that is the alkene, is supra partner and the second partner, that is the ketene, is an antera partner. So, 2π supra and 2π antera mode of cycloaddition reactions between the alkene plus ketene. So, let us see the example. These are all the proven examples. Yeah. So, this is a ketene molecule and this is an olefin. So, what happens generally as per the pericyclic reaction means cycloaddition takes place between these two, where this is a 2π partner and this is again a 2π partner, right. So, the olefin acts as a supra partner and the ketene acts as the antera partner. So, therefore, these reactions are shown as 2π supra plus 2π antera cycloaddition reactions within the square bracket. Now, what happens initially is, so the orbitals are there for the olefin in the same plane and for the ketene they are perpendicular. So, ketene is an anterafacial partner, so bond formation takes place in this way, right. This is the cyclic transition state. So, where the carbonyl carbon atom of the ketene is directed towards the more hindered side of the alkene, more hindered side, and the other carbon atom of the ketene is away from the more hindered side of the alkene, right. So, we will get this, which is nothing but double bond O of the ketene and R and H. These are the hydrogens of the olefin. So, we will be likely to see this kind of product on addition of a ketene molecule with the olefin of this type, right. So, next example. Yeah. So, this acts as a 2π partner utilizing one of the pi bonds and this again acts as a 2π partner. So, this is antera partner and this is supra partner, right. So, again cycloaddition reaction takes place here. So, resulting in the formation of the product like this. And now, this is an interesting example. You see this is an alkyne. So, this alkyne, though it is having two double bonds, it can make use of only one double bond and therefore, should be treated as a 2π partner, right. So, any alkene in the 2π partner of alkene plus ketene reaction should be suprafacial only, the alkene should be suprafacial. So, now this is the ketene molecule, again a 2π partner, but it is an anterafacial partner. It results in the formation of double bond O, Cl, Cl, CH3 and CH3. So, if you remember correctly, in the previous class we have discussed some kind of this molecule in the preparation of a ketene molecule again. So, that means again it undergoes electrocyclic ring opening reaction to give a ketene molecule. electrocyclic ring opening reaction. So, you will get to see this ketene molecule after the electrocyclic ring opening of this cyclic product. So, the first step is the cycloaddition reaction and the second step is the electrocyclic ring opening reaction. So, similarly, this on treating with C, we are in the presence of triethylamine as the base. So, the first step is the production of or preparation of the ketene molecule. So, this triethylamine, which is a base, so will convert this molecule into a ketene, and the ketene generated will react with this olefin, resulting in the formation of a cyclic adduct product, right. So, you will get to see this one plus C double bond C, Cl, Cl double bond O. So, this undergoes 2π supra plus 2π antara cycloaddition reaction, resulting in the formation of this. So, similarly, cyclooctadiene on reaction with you will get this product. Right. So, the next example is much interesting example and more important also. So, we will see that. So, this molecule on treating with a base, so the base will abstract a proton from here, resulting in the formation of a ketene CH2 or Cl C double bond O. So, this ketene can now undergo intramolecular cycloaddition reaction, and the type of product will certainly depend upon the R groups here. If R groups are the alkyl groups, methyl groups, if R is equal to methyl group, you will get a different product. CH3, CH3, you will get this product, and if R group is hydrogen, we will get this product. And this reaction is highly regioselective. So, you will get to see 42% of this product and 35% of this product. So, what is the specialty of this reaction means? It has an alpha chloro substitution. Whenever a ketene contains an electron withdrawing group like the halogen on the alpha carbon atom, so then the energy of the lumomolecular orbital, which is generally from the ketene, so will decrease in energy. Okay. So, the energy of the lumomolecular orbital of a ketene gets decreased, reduced if there is an electron withdrawing substituent on the alpha carbon atom. If there is an electron releasing group, on the alkene, so then the energy of the homomolecular orbital, which is generally from the alkene molecule, will get raised up. So, now the HOMO energy is increased based on the electron releasing groups attached to the alkene molecule, and the energy of the lumomolecular orbital gets reduced if the alpha carbon atom of the ketene is attached to the electron withdrawing substituents like halogens, right. So, this is an example of intramolecular cycloaddition reaction, which is typically 2π plus 2π antara mode of cycloaddition reaction under thermal conditions with an olefin and a ketene within the same molecule. So, now coming to the photochemically allowed 2π plus 2π cycloaddition reactions. So, in the case of open chain olefin molecules, that is simple, quite simple. Under photochemical conditions, both the partners will be suprafacial and therefore stereochemistry will not be affected. So, you will get a cyclic adduct product. So, if you take small cyclic olefins, alkenes, unsaturated systems, then photodimerization takes place, but not photoisomerization. So, you cannot see cis trans isomerization there, but you will definitely see photodimerization in the presence of a triplet sensitizer. That means the small alkene molecules, cyclic alkene molecules, cyclic olefins like cyclopentadiene or cyclobutene or norbornene. So, they undergo photodimerization reaction in the presence of a triplet sensitizer like acetone molecule. So, acetone acts as a triplet sensitizer there. So, sensitizing these molecules and converting them into the dimers, cyclic adducts, by performing 2π plus 2π cycloaddition reactions under photochemical conditions. Okay. So, this under photochemical conditions in the presence of acetone, acetone is the sensitizer here, you will get to see this dimers. Plus so, these molecules are called as anti-dimers, and you can see such kind of molecules or anti-dimers formed when you irradiate the small cyclic alkene molecules, olefins like cyclopentene or cyclobutene or norbornene in the presence of a sensitizer like acetone. You will get anti-dimers. So, what if you use cyclobutene? So, this cyclobutene again on irradiation, that means under the photochemical conditions in the presence of a sensitizer like acetone, you will get to see the dimer. Okay. So, norbornene again in the presence of a triplet sensitizer undergoes dimerization reaction to give two different dimers. Plus so whereas norbornadiene, so again undergoes 2π supra plus 2π supra cycloaddition under photochemical conditions. So where you will get to see this molecule. So coming to the another example, so this benzene under special conditions reacts with this as 2π plus 2π cycloaddition, resulting in the formation of this product. So one more important example is the preparation of baskettine. So this undergoes 2π plus 2π cycloaddition, where this is a 2π partner and this is again a 2π partner, right. So resulting in the formation of this molecule, which on further several steps will give you baskettine. So this is baskettine molecule. So another important example of cycloaddition reaction between fulvalin and a 2π system. So fulvalin is a 14 electron system. (14π electron system). So 1, 2, 3, 4, 5, 6, 7. 7 pi bonds will continuously involve in the cycloaddition reaction, and this is a 14 pi system. It reacts with tetracyano ethylene tetracyano molecule like this. This is a 14 pi plus 2 pi cycloaddition reaction. So, what happened to the double bonds? So, you will get to see this product. Okay. So, with this we close the 2π plus 2π cycloaddition reactions. Of course, there are so many other examples are there. So, with 2π plus 2π cycloaddition reactions, I would request you to please follow the textbooks like Pericyclic reactions by Professor S. Shankar Raman. So, you can see number of examples, please try to work it out, right. So, in the next class, we will see 4π plus 2π cycloaddition reactions, so the most important one, right. So, we all know, we have already practiced such a kind of reactions which we know in the name of Diels-Alder reaction, but what we need to know is Diels-Alder reaction is a thermally allowed pericyclic reaction, cycloaddition reaction resulting in the formation of a cyclic adduct, right. So, we will discuss elaborately the 4π plus 2π cycloaddition reactions in the next class. Thank you.